So we are continuing our discussion on one proportion z-tests. We're still doing problems with just a single proportion p. Last video, we talked about one-sided tests for p, where it was just a greater than or just a less than sign. But in this video, we're going to talk about p problems where you have a two-sided test or a not equal to alternative hypothesis. So we've already gotten into how you find your test statistic, and we talked about all the details for setting up a four-step. We're doing all that same stuff, except instead of having a one-tailed test. So our potato truck problem, for example, had a greater than HA. We looked at area going this way. Our penalty kick problem had a less than HA, like you see right here. What we're going to talk about in this video is not equal to problems with our alternative. And as you can see, when you have a not equal to problem, you have to worry about being too far off in either direction, so you have a two-tailed test instead of one. Now, just by looking at those three pictures at the bottom of the slide, think to yourself, will my p-value be bigger or smaller when I do a two-sided test? And the answer, so pause if you need a little more think time here. The answer is that your p-value is going to be larger, twice as large, in fact, because you have to worry about both sides being off by too much this way or also this way as well. So not equal to problems have larger p-values in general, which means that they are going to take more evidence before you're allowed to reject HO. So it's harder to reject your null in general in a two-sided test. So we're doing one big example in this video, and it's kind of a cool example that I learned about from reading our textbook here. It talks about a rule called Benfords Law. And Benfords Law is one of many tricks that accounting companies can use to detect fraud in documents. So when people are like making up numbers in their financial documents to falsify their tax records and stuff like that, there are a lot of different things that like the IRS and stuff like that can do to catch you. One such rule is called Benfords Law. And basically what Benfords Law says is if you look at the numbers on top of different finance records, you would, like me, you, some average person who didn't know any better, would expect that about the same number of documents start with the number 1, start with a 2, start with a 3, 4, 5, 6, 7, 8, 9, 0. So we would expect to see about 10% of our documents starting with each of those numbers. Seems reasonable to me. But according to Benfords Law, it's actually a lot more common to have a document starting with the number 1. 1 is actually the starting number of about 30% of documents, as opposed to the 10% if you didn't know any better. So it's kind of cool. If I'm a company guy, if I have my own little company and I'm trying to make up my documents here, make them look good so I don't get in trouble with the IRS, I probably will make sure I have about the same number of 1s, 2s, 3s, 4s, etc. When actually, if you didn't know any better, 1 is actually supposed to happen more frequently. So they are looking in this situation here. They are going to analyze this company, and they are going to look at the proportion of documents that start with the number 1. So the true proportion of documents at this company that start with 1. Now, when we set up our hypotheses here for this problem, we go in assuming that nothing fishy is going on here. We're looking for evidence that actually something weird is happening in this situation. Nothing fishy would happen if the true proportion is 0.301, like Benfords Law says it should be. If you're an honest company, probably around 30% of your invoices are going to start with the number 1. And then we're looking for evidence that this company actually is up to something suspicious. Now, if too few of their documents started with the number 1, if it was around 10% or whatever, that would be suspicious. But it also could be suspicious if like 50 or 60% of their documents all start with the number 1. So this is a problem where it does make perfect sense to do a not equal to alternative hypothesis, because both directions, too low or too high, would be kind of a signal that something is up in this problem. So sometimes it makes sense that you need to do a two-sided alternative. So this is going to be my setup for this problem here. I also need to establish an alpha before the problem begins. So I need to set my threshold for what evidence is going to convince me before I even start. The problem doesn't tell me what to use right here. I'm going to mix it up. Last video I did a 0.05. This time I'm going to go 0.01 because before I flag this company, I want to be pretty sure. You could do a 0.10 or something like that as well. It's really up to you what you set that alpha as. But whatever, I'm going to go with 0.01 for this example. Then we're going to check our conditions here. For our conditions, I need to first of all check to make sure it's a random sample. And they say that it is a random sample of 300 documents. So that's good. 300 is definitely less than 10% of all documents at this company. That's reasonable to assume. And then I need to also check my NP and 1 minus P. I do not advise you put the letters. I just recommend you plug stuff straight in. N times P, and you take your P from HO. So 300 times a 0.301 is about 90.3. That's greater than or equal to 10. And then 300 times 1 minus that is about 209.7. Also greater than or equal to 10. That means sampling distribution of p hat is approximately normal, so we are good to go. So that is my condition check. Now, I could do a problem right here where I set up my little curve, I find my p-value by hand. I want to talk about it, but I'm not actually going to do it this way. If I was really doing this the full work way, they got 68 out of 300 digits that were starting with 1. 68 out of 300 means that their p-hat was about 22.6%, 2267. So they were supposed to get 0.301. They got 0.2267, but because it's an alternative hypothesis that is not equal to, I would not only wrap up this area, I would also need to worry about the corresponding area on this side. So to figure out what that is, what I would need to do is figure out about that much to the right of the picture. So if you do just math on that, this number ends up being 0.3754. So this distance is the same as this distance right here. I would want to find equally surprising evidence on that side. And I would do my normal CDF and I could double the area or just do each of those. You also could go the z-score route, where you find a z-score test statistic for 0.2267 and then just do it that way as well with both sides of the problem. I'm going to pause and come back with that test statistic because I want to cut a few seconds off this video. All right, so if you actually calculate that test statistic by hand, you get negative 2.806. When you get a test statistic, you should already in your head be thinking if your results are going to be significant or not. 2.806 standard deviations is pretty far from the center at 0. So I'm already thinking, before I even get my normal CDF, that my p-value is going to be pretty low for this problem because I got a relatively high test statistic. And I would need to find both of those areas same way I would do right here. So that is the beginning of my problem. I'm going to show you guys the calculator option though, so that way we can actually practice that a bit. So if I pull that up here, I would go stats, tests, and I would do a 1 prop z test. This time I have 0.301 for my HO. I got 68 out of 300, and it's a not equal to HA. If you calculate that, it's going to give you some information right here. So I'm going to go ahead, and for the do step, I'm going to show you what you would do if this was just by the calculator. You write down the name of the test first. It's a 1 proportion z test. And then you're going to report your test statistic, which was negative 2.807 if you round it. You're also going to give the p-value for this problem. The p-value in this problem was about 0.005. So this is what you need to come back with in reports. Then we're going to write a conclusion based on that. So why don't you pause and try to write a conclusion yourself, and I will pause and come back with what it should say. All right, so I got my conclusion with a nice little script written right here. Remember, what you do is you say there's convincing evidence or there's not convincing evidence for HA. And HA was that P is not a 0.301. So when you do these problems, sometimes you get like a double negative or something like that, but just write HA in context. There is convincing evidence that the true proportion isn't 0.301. What does this mean? Well, does this mean, okay, lock them up, these people are definitely doing something illegal, something is fishy right here? Of course not. There could be an honest explanation for why they're so off from what Benfords Law says they should be. But what this would be not even a person doing this. This would be like a computer program that you would just feed the documents in and it would pop back out and answer. And if you talk about like, you know how like electronic documents, stuff like that, sometimes you get red flagged for something and the system says, hey, we need like somebody else to take a look at this. A red flag would go up by the computer company, the accounting company. And then a person would be like, hey, maybe I need to do a little more research on this company and see if something actually is going on. So this would be like the first step in the process. There'd be a red flag on their account, and then they would go and do more research. So when the IRS actually like scans people's taxes and stuff like that, I don't know this, I'm assuming this, there are all sorts of red flags like this one that the system would kind of alert them to, and that's how they decide if they're going to audit you and do a more thorough investigation. So the last thing in this lesson, it is actually possible that I could have answered this problem with a confidence interval instead of doing a significance test. So you can use a CI on two-sided tests. So what do I mean by that? Well, if you have a two-sided test or a not equal to test, I'm actually going to tab back to the first picture real fast and show you guys this example right here. This should look pretty familiar to you guys, except when we were doing this back in chapter 8, we were concerned about this area in the middle and not the area on the edges. But what we would do is we would say, oh, if we want a 95% confidence interval, that means 95% of the area is in the middle. Or in other words, 5% of that area is in the tails. So actually, a significance level of 0.05 for your total p-value right here is the same thing as doing a 95% confidence interval. If I wanted to make this a 90% confidence interval in the middle right here, well, that means this is 0.05, this is 0.05. That's the same thing as a significance level of 0.10. So there is very much a connection between a confidence interval and your p-value alpha significance level stuff if it's a two-sided test. We can't do it on one-sided tests like this because confidence intervals always take that middle part and leave out both edges. So anyway, if you have a two-sided test, you can use a confidence interval. Why would you want to do that? Well, a confidence interval gives more information than a significance test does. In a significance test, we come back with, hey, it's probably could be 0.301 or it couldn't. We just get a verdict and that's it. If you do a confidence interval, it actually gives you a whole range of plausible values on top of being able to make a verdict. That's probably a little bit confusing. So what I'm going to do is I'm just going to run a one prop z interval like we did last chapter. I'm going to take that same 68 out of 300 and an alpha equals, I did 0.01 for this problem. So that would be the same thing as a 99% confidence interval. If I calculate that, it's going to spit out an interval from me, and it goes from 0.1644 to 2889. So we have 0.1664 to 0.2889. So this is what I would get. I guess I left 95 right here. I would do 99 since I did a 0.01. So just making it match. This is going to be my interval for this problem. Well, if you think about HO, HO was that the answer is supposed to be 0.301. And 0.301 is not inside of this interval. So there is convincing evidence. The answer is not 0.301. It's that kind of convincing evidence thing we would do last chapter, where you check if your number is inside that interval. So confidence intervals can be more helpful. Not only can we make the same conclusion, oh, there's convincing evidence, it's not 0.301, but we also get the added benefit of an interval of what the answer actually could be. So confidence intervals can sometimes answer the same questions as significance tests if it's a two-sided test. And the benefit is that you get a bonus interval for what it could be on top of being able to make your decision.